So we're going to talk about how to solve linear systems that have non-real eigenvalues, so complex eigenvalues. So here is an A from a matrix vector system of x prime equal ax, and we are going to compute a minus lambda I, so 1 minus lambda minus 4, 2 minus 3 minus lambda. Find the determinant of that, which would give us a lambda squared, a 3 lambda minus 1 lambda, so plus 2 lambda. And then we have a minus 3 plus 8, which is plus 5 equals 0. So this is going to require the quadratic formula, and we would have negative b, so 2 plus or minus the square root of b squared, which is 4, minus 4 times a times c, all over 2a. Well, 4 minus 20, this would be square root of negative 16, which would be 4i. Now we've got the eigenvalues, but we're going to reduce them all by 2 here with that 2 on the bottom, so negative 1 plus or minus 2i. So two eigenvalues, complex conjugates of each other. So now let's go ahead and find an eigenvector. So let's take our matrix A minus lambda I, we're going to put in negative 1 plus 2i. So if we have negative, negative, make a positive, that'll be 2 minus 2i, negative 4, 2, minus 3, minus makes plus, negative 2, and minus 2i. Now we augment this with zeros to find eigenvectors, and I'm only going to do this once so you can see what happens, and then we won't have to mess with it after that. We know there should be a dependency because we figured this out where the determinant was 0. Not obvious to see that dependency right here, so I am going to do some row operations so you can see. I think I'll just do 1/2 row 1 and 1/2 row 2 for a minute, just to kind of reduce those down because there's a 2 in everything. 1 minus I minus 2 and 1 and minus 1 minus I. Now if you're wanting to do row operations and you have a complex number and the corresponding element in the other row is not complex, you can always multiply by the conjugate to get a non-complex number. So I'm going to use that strategy here and show you what happens. So I'm going to multiply row 1 by 1 plus I, which is the conjugate of the 1 minus I that's there. So I'm just going to go up the top to do that. If I had 1 plus I and 1 minus I, first times first will give us 1. Outers and inners always cancel on conjugates. One's a plus I and one's a minus I. Last times last is minus I squared. But we know I squared is a negative 1, so this becomes 2. And then in the next, if we multiply the second element by it, we would have negative 2 minus 2i. And you can see that was exactly what we had before we reduced it by 2 here in the first. So you can see if we did negative 2 times that added to the other one, it would zero out the other row. So there is a dependency. It's not easy always to see, but we don't, since we know there is a dependency, we don't need to really even do the row operations. We can just take the first row, and I'm going to take it actually in its reduced piece right here, and we can put the variables back in to find an eigenvector. So I have 1 minus I v1 minus 2 v2 equals 0. So moving that over, 1 minus I v1 equals 2 v2. So for picking an eigenvector, we want to make something that's easy. So if I let v2 be 1 minus I, then those would cancel when I put that in there, and it'd leave me v1 is 2. So there it is. And we are going to want to express this split up, so I'm going to do that right now. The real part is right here, and then the imaginary part would be 0 and negative 1 squished right there on the edge. So now we can build a solution if we take e to the lambda t multiplied by the eigenvector. And it turns out that if we need an eigenvector for the conjugate, so the -1 minus 2i, if we take a minus lambda 1i v1, we could take the conjugate of each piece, and that's what this bar over it means. And the conjugate for lambda 1 is lambda 2. And so the eigenvector that would correspond with lambda 2 is the conjugate of the eigenvector 1. So if we needed another eigenvector for the second one, we could do 2 because the conjugate of 2 is still 2, and 1 plus I because that's the conjugate of 1 minus I. But it turns out if we build those, we're going to see how to build the solutions, but in the end the solutions that are built end up not giving us any new information for the conjugate, so we can get two linearly independent pieces and build all solutions, and it would cover both for the complex eigenvalue and for its conjugate, which is just going to end up being a scalar multiple. So it's all going to be able to be done with our e minus lambda t times by the eigenvector. So let's see what that's going to look like if we did it with the complex. It's going to be e to the -1 plus 2i, and the -1 again, like I said, we're going to end up getting the same type answers, so we don't worry about the plus or minus t, and then multiplied by the eigenvector 2 and 1 minus I. Now, a couple of things. Let's remember how we did Euler's formula to express this in terms of using also sines and cosines, and so that's what we're going to want to do. So we're going to have e to the -t. If you remember, this book uses alpha and beta, so if our complex number is alpha plus or minus beta I, remember the alpha goes in front of the t, so in this case that's a -1. And then we have multiplied by, we have cosine of beta t, in this case it's a 2, plus I sine of 2t, and then that would need to be multiplied by this eigenvector, and actually I'm going to have it split. So here was the real part, and then plus the imaginary part. So what this is going to involve is it's going to need to be FOILed. We have two terms here and we have two terms here. We're going to go on the next slide to look at that. So this is what we have, and we want to see about multiplying this. And what I'm interested in is kind of getting the solution there, but then rounding up kind of the real parts and the imaginary parts. So if I'm doing this, the e to the minus t is out in the front and it goes on everything. So if I multiplied the first to the first over here, I would have 2 cosine 2t, and then for the bottom, the second function, I would have a cosine 2t. Now if I'm looking for kind of what's going to be real when I multiply it, and that's going to be real, and then over here I'm going to have an I and see what's going to be imaginary. If I multiplied the cosine t over here, it would have an I on it, but it's going to be 0 for the top, but the bottom is going to be minus cosine 2t, so that would go right there. Let me just slide that over so I got room, minus cosine 2t. So now I'm going to multiply the I sine 2t over here, so it's going to put an I on that. So with the i's, I'm going to have a 2 sine 2t, and also on the bottom I'm going to have plus sine 2t. And now if I do this last one to the last one over here, I'm going to have an I from this one and an I from that one, which is going to make I squared, which is -1. So it's going to be a real term, change signs, have a negative on it. And so the first one's going to be 0 for the upper one, but the bottom one is going to be minus and then a minus from the I squared, so that'll make that a plus sine 2t. Okay, so when we did that foiling and we got that, then this is essentially what we have. And I should have I meant to have parentheses around all of this. The E applies to all of that. And so we have the real part and the imaginary part. If you remember when we talked about complex roots, when we were solving second order differential equations, we checked it out and we learned that if you have a complex solution, has a real term and an imaginary term, then it's also true that the real term is a solution by itself, and the imaginary term, not with the I, but just the imaginary part there, it would also solve. And so we're going to take those two pieces, and that's how we're going to build all of our solutions. So here's our two pieces, and if we take just the real part and put it in a linear combination with just the imaginary part, then we would have all solutions. So these are the solutions to the system of differential equations. Now, I wanted to show you kind of what we did when we multiplied that out in general, so we can look and see how to do that, and we can either sort of memorize what ends up where, or if you do it in that sort of its generic form first and then put the numbers back in, it's maybe a little bit easier to see. So this will be on the front, so I'm not going to worry about that part. I just want to write down the things we were doing with the foiling. So if we have cosine and we have beta t, I'm just going to do it generically, and I sine beta t, and we foil it. I'm going to call this P, vector P. P is the real part of the complex eigenvector, and then plus IQ. Q is the complex, the I piece of that. All right, so if we were to FOIL this, we want to know which stuff ends up being real and which stuff ends up being imaginary. And you can see that cosine times the real part of the eigenvector is going to be real, no I in there, so it's going to be cosine beta t times the real part of the eigenvector. And then if we did outers, this is real, this is imaginary, so it's going to be imaginary, so that's going to be cosine beta t times the imaginary part. Now we're not going to put the I in, because remember, the real part and the imaginary part will both solve it, and we'll put them together in a linear equation. Okay, if I did inners, there's going to be an I on it, so that's going to go over here in the imaginary, so that's sine beta t multiplied by the real part. And then if I did last times last, that's when we get the I times the I, or I squared, and that's why it's a minus here. And then it's sine beta t times the imaginary part of the eigenvector. So that's how we're going to build our solution, the real part and the imaginary part, and then we're just going to put them in a linear combination so that we have the complete solution. So here's kind of a summary of that. When we have complex conjugate eigenvalues and our eigenvector is p plus qi plus or minus qi, that covers both eigenvectors, then we're going to build the solutions by taking the real part and the imaginary part and putting them in a linear combination. The real part we just saw was going to come from, and we need to put those e's on there now. I was just looking at the foiling part, but it's going to come from the cosine term, will be with that real. This one came from, there was an I on the sine term and an I on the q of the eigenvector, so that made that a -1, so it's a real term. Then these are the others that are going to have just one I on them, so they're going to be part of the imaginary solution. This had an I on the sine, this had an I on the q. So let's go back to the solution that we had for this first one, and let's see what this solution would look like if we were trying to figure out what it looks like graphically. So these are parametric equations. Let's think of it as x and y. So x is the upper pieces of this thing, and y is the lower pieces, right? And so both of those involve a sine and a cosine. They do have the same argument, so that would think of if you were parametrically had 2 cosine t and 2 sine t and you plot it on an xy plane, you would get a circle. Now, the cosine and the sine want to oscillate, but the e to the minus t is something that is decreasing and going to 0, and that'll be multiplied to it, so that'll affect the amplitude. So if you're looking what x is doing, it's wanting to oscillate, but the amplitude is becoming smaller and smaller, and y is doing a similar thing. So this is what it looks like when it is graphed. These are various solution curves. There's 1, 2, 3, 4 of them, just trying to show, and they want to circle because of the trig functions, but the amplitude is decreasing and going to 0. And so you can see there's an equilibrium solution right here in the center, and they are circling around approaching that. So this is called asymptotically stable, that equilibrium solution. Why it's asymptotically so is because if you keep zooming in, you're still circling around, but you're getting closer and closer to it till you get so close you can't tell the difference. But so we're approaching it in this circular way. Now that was because the eigenvalues had negative real part, which made our e to the negative t's, which is going to go to 0. Okay, let's look at another example. To solve this one, we're going to do 1 minus lambda, 2 minus 2, and 1 minus lambda. Take the determinant. We've got lambda squared, minus 1 lambda. Nice. Another one is minus 2 lambda. Minus to minus makes a plus 1. Minus to minus makes a plus 4, which is plus 5. So this looks very similar to the other one, just has an opposite sign right here. Now the thing that's going to do is change the sign on our real part then, because when we do negative b, that's going to be 2 plus or minus the square root of b squared minus 4 times a times c all over 2a. Very similar, so the eigenvalues are going to be 1 plus or minus 2i. So the real part now is positive instead of negative. Okay, let's go ahead and find an eigenvector to go with that, and then let's see if we can build the solutions. So we're going to use eigenvalue 1 plus 2i, and so 1 minus 1 is 0, so this will just be minus 2i, and then 2 and minus 2 and minus 2i. All right, so if I put the variables back in to find an eigenvector, I'd have negative 2i v1 plus 2 v2 equals 0. Let's divide by 2 and move 1 over. So I have I v1 equals v2. So the eigenvector, we're going to choose I for the v2, and that means v1 would be 1. If I broke this down then into the real and imaginary, here is the real part, and then put the I, and the imaginary part is 0, 1. So this is like my P, and this is my Q. Okay, now let's go ahead and build the solution then. The solution is going to come from the real part and the imaginary part there, and combined in a linear combination. So we're going to have C1 e to the real part of the eigenvector is 1, so just t, and that's going to be multiplied by real parts would be cosine, our beta is 2t, and then I need to multiply that by the real part of the eigenvector. And then the other one was where we had the I times the I, which gave us the I squared, so it's negative, and it was when we had the sine of 2t multiplied by the imaginary part of the eigenvector. All right, and then with that we're going to have, so actually that's our first part, and then we're going to have c2 e to the t multiplied by, so if we had sine of 2t multiplied by the real part of the eigenvector, that would have had an I on it, and then plus cosine 2t multiplied by the imaginary part of the eigenvector. So here is our solution, and it came from those pieces. We added the real and the imaginary in a linear combination, and this is what ended up real and what ended up imaginary, so we got those in there. Now let's see what that one's going to do. Now because well, let's look back at our solution again for a minute here. And so we can see that we've got sines and cosines again, so we're going to get that circular motion. But what is the amplitude going to do this time? Well, it's e to the t. As t goes to infinity, that's going to keep increasing. So this is going to want to circle, but then with increasing amplitude. So it's going to spiral again, but it's going to spiral out. So these are going away from the origin. And so this is an unstable equilibrium solution, and that was because it had a positive real part, so it had that exponential that's going to increase. This is then called unstable. Okay, let's look at one more example. So we're going to take a matrix and do our a minus lambda I thing again. -5 and 1 minus lambda, and we get lambda squared, and then we have -1 plus 1, so the middle cancels, and then we have -1 plus 10, so plus 9. So we can figure out where that equals 0. That's when lambda squared equal -9, so lambda is going to be the square root of that with plus or minus, so 3i. So these are called purely imaginary eigenvalues because the real part is 0. Let's go ahead and take that then. Let's do 3i and see if we can find the eigenvector to go with it. And so that's going to be -1 minus 3i and 2, and -5 and 1 minus 3i. So putting variables back in, I have -1 minus 3i on the v1 plus 2v2 equals 0. So I'm going to move this one to the other side, so I'll have 2v2 equal 1 plus 3i v1. So our eigenvector, let's choose for v2, let's do 1 plus 3i, and so v1 is going to be 2. So there's our eigenvector. Let's write that split into real and imaginary pieces. That's going to be 2, 1, plus the imaginary piece is going to be 0, 3. So let's go ahead and build our solution then. So we're going to have c1 e to the 0t, so that's just going to be a 1, so we don't need that on there. And then it's going to be cosine of 3t because of the 3 right here, multiplied by the real part of the eigenvector minus sine 3t multiplied by the imaginary part. And then I'll put it down below so I don't crash there. So then we need c2, and again it's e to the 0t, so we don't need to list that, times, and we have sine of 3t times the real part of the eigenvector plus cosine 3t times the imaginary part of the vector. So there's our solution, and let's actually list this as x and y so we can see it a little clearer, because this is the vector and our variables. Let's do x and y. So if you need x, you just look at all the upper stuff. So it's going to be 2c1 cosine 3t, and then it's going to be plus 2c2 sine 3t. The other parts of that are 0, so you can see that one is going to want to be circular, except if these c1s and c2s are different values, it will be elliptical instead of circular. And so what would our y be? We're going to have c1 cosine 3t minus 3c1 sine 3t plus c2 sine 3t, and then plus 3c2 cosine 3t. All right, so that was a 3, C2. So here they're just sines and cosines, and so we could actually even write this as C1 plus 3C2, and that would be in front of the cosine 3t, and then we could have minus 3C1 plus C2, and that's in front of the sine 3t. So you can see again it's just a sine and a cosine. They can have different coefficients on this, which would make them, when we do the combination, the x and y on an xy plane, we're going to get this elliptical. So here they are, and this is various solution curves, what they would look like. And interestingly enough, then this one is called stable but not asymptotically stable. It doesn't approach a single value. It's going to continue to have this elliptical orbit moving around. So it's not going to blow up. So they don't consider it unstable, but it's not going to approach one single finite value. And so this is called stable but not asymptotically stable. Okay, so just in summary then, 3 things can happen when you have complex eigenvalues. You can have a negative real part, which basically causes this to spiral around and towards the origins. So that one was asymptotically stable. You could have complex eigenvalues with the positive real part, so that one would want to circle around but then have increasing amplitude, and so that would be spiraling out, and that one is unstable. If you have complex eigenvalues that are purely imaginary, so the real part is 0, then they're going to want to cycle around in an elliptical pattern, and those are stable but not asymptotically stable.